Cue the theme song. There's still no music. Oh, well, that just got real awkward. But we arrived at your first major theorem in your advanced mathematics career. The fundamental theorem of calculus, part 1. Whenever I read this, I think of the Star Wars theme song. If you're a Star Wars nerd like me. Because it's that powerful. Okay. So, before we even get into this, a little background knowledge. Isaac Newton decided to discover this, or define this for us, a couple of centuries ago. But it takes this idea of differentiation and builds a bridge. That's not a one-way bridge, but a two-way bridge between differentiation and integration. A practical example before we get to the more formal definition is the definite integral of our parabolic function, which at this point we should know will operate accordingly, right? X cubed divided by 3. We would substitute in these bounds accordingly and subtract them to determine that the area is 93, right? However, also observe that capital F of x, x cubed divided by 3, is an antiderivative of the function. So we can also write that the definite integral from 4 to 7 of x squared dx is simply equal to capital F for the outputs of the bounds of the antiderivative. Okay. Now you might be sitting there on your bed, on your couch, in your comfy chair, at your kitchen table, in the backyard, at Starbucks, or wherever you're watching this. And you might be saying, well, you've been doing that for like 2 lessons now. Which is true. But now we at least have a solid base as to why we were auto-assuming that we were allowed to do this. So, what does the fundamental theorem of calculus part 1 say? It says that assume that f of x is continuous on AB if capital F of x is an antiderivative of the original function on AB, then the integral from a to b of f of x dx is nothing more than the bounds as outputs of the antiderivative. In layman's terms, right, all this symbolic notation is just saying that the definite integral is the difference of the antiderivative values at the upper and lower bound limits. Which is, once again, something that we've been doing. Now, the proof of the fundamental theorem of calculus involves Riemann sums, which, like I said, is a topic that I will reserve for your professors. But, if we wanted to, and of course we want to, let's look at a little bit of application of this. Right? Calculate the area under the graph of our cubic over 4 using the fundamental theorem of calculus, part 1. Okay. Well, in order to use the fundamental theorem of calculus, we need to first define the antiderivative. So capital F of x is equal to x to the 4th over 4. So the definite integral of our function is equal to, once again, the difference of the upper and lower bounds as inputs. So we really have x to the 4th over 4 from 2 to 4, which is, and I'll let you handle the arithmetic, but we get 60. Okay. Now, this entire process is tedious. Very drawn out. For all intents and purposes, I've never really come across a professor, faculty member, or myself who require you to do it in such a disjointed manner. Instead, let's take a look at another one. Let's say we had 1 to 3, x to the negative 3/4 plus 5x to the 5/3. Or is that 3? That is 3. dx. Okay. If we decide to anti-derive this, why not put this? Okay. Or we can just simply substitute our bounds in now. We don't necessarily need to first establish, okay, here's my antiderivative, okay, then let's write this, then let's write capital F of 3 minus capital F of 1, okay, now we're going to write this, so on and so forth, okay? We can integrate, and we can plug in our bounds, right? So we're going to plug in this with 3, and then we're going to subtract that same expression with 1. It's clearly gnarly, so I'm going to spare you and myself. But if you wanted to work it out, the value is 21.2. Now, let's take a look at an interesting one. Zero pi sine of x dx. If you think about this as a unit circle, your intuition should tell you what the area is of this function. And if you are not, that's also okay. The integral of sine of x will be negative cosine of x, once again from 0 to pi. So we have negative cosine pi minus negative cosine of 0. So we're going to have a plus plus here, which will yield negative times negative 1, which will yield positive plus 1, which is 2. Okay. Don't forget that the definite integral has signed area pre-programmed, okay, between the graph and the x-axis. Okay, because if we take a quick, or we make a quick sketch, and we're going to do another sine integral, but the sine function looks like this: 0, pi, 2 pi. So this situation here is an area of 2, as confirmed by this. But what happens, or what should happen when we have 0 to 2 pi? Well, we'll take 2, and since it's circular or periodic, we know this is going to have an area of 2. We're going to subtract those, so we should get an area of 0. Plus, it's symmetrical. So, once again, rinse and repeat. Negative cosine of x from 0 to 2 pi. Negative cosine of 2 pi minus negative cosine of 0. Bang bang, 1. It's be negative 1 plus 1, which is 0, just like we had anticipated. And what makes any of this actually possible? The fundamental theorem of calculus. Right? The fundamental theorem of calculus is what tells us that, hey, if you find the antiderivative, the definite integral of the original function is nothing more than the upper limit minus the lower limit as they're substituted into our antiderivative. Okay, this is the glue that keeps all of this nice and cohesive. It's a quick video, but I'm going to leave you with one to do on your own. Two to 8 dx over x. Final answer is natural log of 4. What mysteries await in between our integral and the final solution? I'll leave that for you. Good luck. See you at part 2.